We have a plot of just the concentration versus time. It produces a straight line, which means we're dealing with zero order. And it has this slope, okay, and it's asking for the time. All right, so we know that this is zero order. So I'm gonna write out their integrated rate law here. Okay, and I'm going to show you that this is also in a y equals mx plus b format, okay? So that's why we can talk about things in terms of how they look on a graph. And if our slope is m here, it'll be negative k. It also tells us our y-intercept, or no? No, it doesn't. It asks us how much time is required for all of this to decompose. So we want to get from our initial concentration here being 1.25 e to negative 2, and we want it to become 0, right? We want to decompose all of it. So when you do this, you should get your times equal to 312.5 seconds. Always keep everything in seconds. Any questions on this one? Okay. For the next one, it's a conceptual one. So we're dealing with an electrolytic cell. Okay. And here's our temperature. Which of the following statements are true? And we have these two half reactions. A is saying electrons will be sent through this salt bridge. That's already wrong. We know that ions are sent, and specifically if it's going to the cathode, it'll be cations. B is saying the potential of this electrolytic cell indicates that the reaction is non-spontaneous. And that is true because we are going to get a negative cell potential. Specifically, if you wanted to calculate it, it would be the difference between these, and it would be the negative difference. So 0.14. Negative 0.014. The next one is saying the mass of the SN will increase. So first thing we want to do is label which is the anode and cathode. And in electrolytic cells, the one with the lower SRP is going to be the cathode this time. So this is the cathode. And it's saying the mass of the cathode electrode will increase, and that is true because those properties still stay the same. The anode is going through oxidation, cathode is going through reduction. D is saying the SN material or metal will become reduced in this reaction. And that is not true because of a small fact, okay, here. Not the metal, but the ion, the SN2+. Okay, so we want to remember what exactly is reacting, not the metal, right? And that's why the platinum can work, because it's not part of that reaction. It's not being reduced. The ion is being reduced and turning into the SN metal. And the last one is saying this type of cell does not require a power source since it is spontaneous. And that is false because it does require a powered source because it is non-spontaneous, okay? So any questions on number 2? Okay. So number 3, we have these experiments and it's asking for the rate constant with units. Okay, so if we use our isolation method, we want to find experiments that stay constant in A and then change in B, or stay constant in B and change in A. So if we look, experiment 1 and 3, A are constant, B is changing, and so is the reaction. It is doubling. So it has that proportional relationship. So we know B is first order. Let's isolate reactant A. and see where B is constant, and that would be experiments 3 and 4. And we see not only is it doubling, it's quadrupling, right? The rate is increasing, sorry, 4 times, and we know that's going to be second order. Okay. Then all we need to do is find the rate constant and input those values. So I'll just choose experiment 1. That should be your setup, and all you need to do is solve for K. And you should get 0.01 molar. And then you might ask yourself about the rate constant units. And so that would just be, sorry, I don't know why it was molar. So that would be, because we're dealing with third order here, molarity 2 minus times seconds minus 1. Any questions on that one? Number 4, it's asking about collision theory. For A, it's saying there is a specific orientation which reactants must collide, and that is true, right? Orientation is very important. The next one is saying only energy is needed for collision theory. That's not true, right? We just stated that orientation is also important. C is saying that activation energy can be positive or negative, and that doesn't really make any physical sense. It can only be positive. So, and the last one is saying, or in D is saying, if there is any collision, some product will form. And we talked about how we need the proper molecules, we need the proper energy, the proper orientation. So that is not true. And the last one is saying the higher the temperature, there will be more but slower collisions. There will be more but faster collisions. So that'll be false as well. Any questions on this one? For number 5, we have this experimental data, and it tells us that this last one gave a linear plot. The curved plots we can basically ignore. They don't really tell us anything valuable. So we know we're going to be dealing with a second order reaction. And when we're trying to figure out what to put in our rate law, in our rate law, we're not going to consider the products, right? The products don't help us make the products. The reactants help us continue and proceed the reaction. So we only care about the reactants, sorry. And we know it's going to be second order. So therefore, this is the only one that's right. Any questions on this one? The rate law for 2NO plus Cl2 goes to the products is this rate here. So we have our rate law. And it's saying which of the following will change the rate constant K. So this is not really important. But it's asking which of these influence K. We kind of talked about that earlier. Pressure doesn't do anything. Volume has to do with pressure. That doesn't have to do anything. Increasing the temperature, that does, right? So temperature is important. Increasing the concentration won't do anything. And the last one, decreasing the temperature. Again, temperature is important. So temperature and activation energy are the only things that can influence K. You might ask about the Arrhenius factor. That is an experimentally determined constant to compensate for that calculation. And so that is different for every single reaction. 7, what mass of magnesium is produced when molten magnesium iron is electrolyzed? Okay, so we have some information here. We have this compound here, and we have our coulombs per second and our time. This will allow us to calculate anything we need. And this is asking specifically about mass. Okay, so this compound here can tell us how many electrons we need to use. In this case, it's going to be two electrons because magnesium has a +2 charge. And sometimes it'll tell you things. Let me think of an example. There was one I came across today. It was, maybe let's say chromium, and it had 3 oxygen. And so you kind of need to find what the oxidation number is for chromium if you're trying to calculate the mass of chromium, let's say. And so this would have a -6 charge because we have 3 oxygen with each of them has a charge of -2. That must mean this must be a +6 charge if this overall is 0. We would need 6 electrons in that case. But here we're only dealing with 2. So we want to start with our time. Usually you want to start with time if you're looking for mass, or if you're looking for time and you have mass, you start with the mass first. So that's usually like the easier way to do it. I'm sure you can do it other ways, but this is, I guess, the easier path to go down. But whatever works for you. So I'm taking the time, and we want to convert everything to seconds. Letting the units guide you as you go. So cross off those hours. In 1 minute, there is 60 seconds. And in 1 second, we have 3.27 coulombs and 96485 coulombs per 1 mole of electron. That's Faraday's constant here. For every 2 moles of electrons that we got from over here, there is 1 mole of magnesium. For every 1 mole of magnesium, we have 24.3 grams. So again, we can cross off all of our units, letting the units guide us. Keeping in mind the essential knowledge that this amperage is giving us coulombs per second. And what else? We have our molar mass. Our Faraday's constant tells us coulombs per mole of electron. So when you multiply everything on top, divide by everything on the bottom, you should get 23.57 grams. Okay, any questions on this one? Okay, for number 8, this is a conceptual question. We're dealing with a galvanic cell, and it's asking, how do we decrease the potential? Okay, and you can kind of consider the potential like the amount of work or the amount of free energy you can get out of it. It's related. So that's kind of the way you want to be thinking about this. So we want the reaction to go backward if we want to decrease the potential, or we want to drive it. We want to have it favor the backward reaction more. So to do that, we need to figure out what is the reaction in general. And to do that, we need to recognize this is the anode, this is the cathode. We're dealing with a regular galvanic cell, that's why. And when we put everything together, this is what we get. The solids don't participate in the concentrations and the reaction in that way. So we will just take a look at what's happening to the copper and the zinc ions. The first one is saying to decrease the copper 2+. That would work, right? We're going to drive Le Chatelier's, backward. B is saying increase the mass of copper. That doesn't really influence, what we're really looking at is Q, right? Q, because we have this equation to deal with. Okay, so We don't really deal with masses when we're considering these concentrations. Obviously, if you run out of the mass, that's a problem. But that's not necessarily the case here. We're just concentrating on what happens to Q. The C is saying to increase the zinc 2 plus. That would work, right? If we increase this, it would drive the reaction backward. D is to increase the copper 2 plus. That wouldn't really help, right? That would drive the reaction forward. The last one is saying replace the electrode of the cathode with platinum. As we know, that does not affect the cell potential. And you're not expected to know what it would do at the anode. So Ali asks why B won't influence the cell potential. And my answer is right here, because it doesn't influence K or Q. It doesn't influence Q. It doesn't participate in Q because it can't, it's not constant. There's no concentration that we can work with. So that's really ultimately why. The only time it will affect the reaction is obviously when we run out of, let's say we run out of the copper, then we can't continue, you know. Okay. Would the answer be different if we were dealing with an electrolytic cell? Yes, it would, because we're doing everything kind of in reverse. And so this balanced reaction here would be flipped. It would be the opposite. Okay. For number 9, we have this plot here. So this is not an integrated rate law. This is actually a reassembly of the Arrhenius equation. Okay. And it's really important we recognize this also has a y equals mx plus b relationship. I'll write out this time. This A represents the Arrhenius factor. It does not represent the concentration. It doesn't represent a concentration of reactant here. It represents the Arrhenius factor. I know there's a lot of A's thrown around, a lot of K's thrown around. So, okay. So we're told we get a straight line relationship here with the slope of negative 654. Where's that slope coming from? So we have y equals mx plus b. Okay. We have a y-intercept of negative 0.17. And that's the first part of the question. In the second part of the question, we get an integrated rate law this time for second order. And it's asking what is the rate with these variables here. For temperature, we're actually going to take this temperature and put it over here. So this will be 298 Kelvin at room temperature, 225 degrees. Okay, so let's kind of write out everything we know. Seems like what we're going to have to do is find our K value, use that K value, that rate constant value, and put it into the second part. So this is the first part and the second part of the problem, okay? So ln of K equals this is simply all we're doing. We're going to solve for K. So when you get K, it should equal 0.0936. And the way I did that, you're eventually going to calculate everything on this side and then put it to you're going to put e to the power of this value here. Okay. That's how you get rid of the ln. Okay, so we have K now, and we have our integrated rate law. We know this is second order. Okay. So we're going to have 1 over our oh, we don't need to do that. No. So it's saying this is our integrated rate law, but we don't need to use it. It's just telling you, the purpose of giving you this information is just to tell you that this is second order. So we're going to be dealing with rate equals K times B to the second power. B is our only reactant, so that's how I know what the rate law is. And I know it's second order because that's the corresponding integrated rate law equation. Okay. And so let's see what we can fill out here. We know our concentration here, we know K, and that's all we need to calculate the rate. So that would be rate equals 0.0297 meters. Molarity per second. Okay. I just want to clarify one thing. On my review session thing, the question about units is purely for K. I apologize for that. The rate is always in molarity over seconds. Okay, just to clear that up. But the K constant, the rate constant, will have all these units like here that are dependent on the order of the rate law. Okay, yeah, I can go over those units again. So for 0 order, it will just be the molarity over seconds. For first order, it'll be 1 over seconds because the molarity is to the 0 power. For second order, it'll be 1 over the molarity times the seconds, or molarity minus 1, seconds minus 1. For third order, which we see right here, because we have 3 reactants, or 3, one thing's 2 ordered, one thing's first ordered. 1 over molarity squared times seconds, or this. Okay. Okay. In number 10, hopefully we don't have any more questions on number 9. So just to summarize, the first thing I did was to use this rearranged equation of the Arrhenius equation. I used it in y equals mx plus b format, and I filled out all I could so I could solve for K. Then the second step would be to use that K into my rate equation, my rate law, and I knew it was second order because it gave us a hint right here. Okay. For number 10, we have a concentration cell this time, and these are the initial conditions. So these are the different concentrations. We have initially this potential, but that doesn't really matter. The time is not really relevant to us either. The only thing that's relevant to us is our final cell potential and our concentrations, right? So I'm just going to set up our Nernst equation like usual. Okay, and I'm going to kind of fill out everything I know here. This is 0, as all concentration cells are. Okay, for Q, it's a little bit complicated. I just wanted to emphasize that the ion with the greater concentration is going to be the reactant, and this is going to be the product. Because, right, we want everything to go to equilibrium. We want the greater concentration ion, to give some of the concentration back to the product, right? We want to even things out. We don't want that gradient anymore. That's how this concentration cell runs. So there's going to be some change, okay? There's going to be some change between this concentration. So if we had an ice table, for example, and the starting one here would be 1.15, we'd have some change, right? Minus x. And we want to find out what that change was. That's ultimately what this question is asking. What is the concentration at the side where oxidation occurs? Okay. And again, oxidation happens at the anode, or in this case, it was the reactants, right? Oxidation occurs. Hold on. Yes, the higher concentration is the one that gets reduced. Yes, you're absolutely right. So this would be the one with the lower concentration. Okay. So then ultimately what we're looking for is this value right here. Okay. We want to put that into Q. We do products over reactants. Okay. We have everything filled out here to the best of our ability, all these values. And we're going to solve for x. When you calculate everything, x should equal 0.218. And then your final answer would be 0.15 plus 0.218 equals 0.368. Okay, so does that make sense? Any questions? Okay. Sorry, I must have missed a question about, for Jacob, you were asking about products. I'm not sure what question you're referring to. In the meanwhile, I will go to number 11. So we have a second order reaction this time, and we have our initial concentration of A. Oh, sorry. Here. Oh, okay. So oxidation, yeah, of course, oxidation will be occurring at the anode, but for concentration cells, we see the higher concentration, the one that has a higher concentration, undergoing reduction. So I can write that down somewhere. It's taking away ions. I get what you're trying to say, yeah. But I think you have it a little bit reversed, Ali. So the side with the higher concentration is going to be turning into the solid rather than, so you have it right though, like the side with the smaller concentration will be decreasing the molarity of the ion, and that would be the cathode side. That's consistent with what we see at cathodes. The side where the ions increase is the anode side, which is in this case the product side, which is the one with the lower concentration. Does that make sense? Okay, well, let me know. For 11, we know we have a second order reaction, and we start out with this concentration, and we say it's 56.7% complete, which means 56.7% of it is gone, not still there, but it's gone. And this has happened in 198 seconds. It's asking how long does it take for the same reaction to go from our initial to 75% completion. So the first step would be to kind of write out what we know. And since we're dealing with time, we want to deal with the integrated rate law. We know it's second order. Okay. We know our initial is 0.96. We know our time, 198 seconds. And our final, which is 0.42, but I'll show you how I got that. So you're going to do 0.96. Well, first you're going to do 1 minus 56.7, 0.56, 0.567, 600. Okay, sorry about that. We want to find what is left, not what is gone. This is gone. We want to find out what's remaining. And we're going to do 1 minus 0.567, and then multiply this by 0.96, and you'll get 0.433. Okay. So we know what to find. We need to find K. That'd be step 1, find our rate constant. Step 2 is use our new K, or our found K, to put it into a new equation, but it's pretty similar. We're just reaching 75% completion. We have the same initial. We don't know what the time is. We know what our rate constant is because we solved for it over here and got, I guess I didn't write it down. Okay, I'll solve for it quickly. We know our final is going to be 25% of our initial because 75% is gone. And that will give us a final answer of time with 454 seconds. Okay. Any questions on that one? So the first part was use the integrated rate law to find K at these certain conditions where 56% of it is gone, and then use the K you just found to input it and solve for time. Oh, is it 41? You should still get the same time. Yeah.